All right, let's take a look at segment distance, but in this case, we're going to look at the distance between points in a two-dimensional sense. I guess we could do a really easy one on like a number line. So if we have like a number line and you have point A that's located, let's say, at -3, and then you have B that's located at a +5, right? Well, what is the length of AB? Well, you'd say 8, right? That's pretty easy. You can just do that in your head. You can just start at -3 and just think about how many steps over 5 is. All right, so that's the kind of the one-dimensional case. Now let's do 2D. Okay, so let's take this particular point right here, and I'm just kind of throwing it out there. That looks like, I don't know, 4, 3. And then over here, let's say I'm at, I don't know, what do you think, 7, 7? Let's say that. Okay, and I want to know this particular distance. Okay, the nice thing about our coordinate grid is that our y-axis and our x-axis are always perpendicular. Right? X represents our horizontal and y represents our vertical. And you may have heard of this before, but maybe not at an entire unit on it. We're going to look at the Pythagorean theorem. Okay? And I'm going to draw these distances, and we're going to figure out what those are here in a second. But the Pythagorean theorem says this. It says that a squared plus b squared equals c squared if and only if you have a right triangle. And I know we haven't talked about proofs, we haven't even talked about logic yet, but let's do a little lesson here. What the Pythagorean theorem really says in all its glory is that if you have a right triangle, then this is true, where A and B are the legs of the right triangle. If you have a right triangle, then if you look at the relationship between A and B, which are the legs, and the hypotenuse C, that a squared plus b squared must equal c squared. And actually, it goes in the reverse as well, that if you can show me that a squared plus b squared equals c squared, then you actually have to have a right triangle. So if you had this triangle and you weren't sure whether it was a right triangle or not, if you showed me that this was true, boom, you know it's a right triangle. Most of the time, we go in this direction. You know you have a right triangle, thus this is true. Okay? And it doesn't matter, obviously, hopefully it's obvious, how the triangle looks, right? The triangle can look like this. That's a right triangle. And again, the A doesn't have to be horizontal. That can be A, that can be B, and then the hypotenuse. In this one, for sure, a squared plus b squared equals c squared because it's the right triangle. The nice thing for us on a coordinate axis is that we always can get a right triangle. So we know that this squared equals this squared, and that's what we want to find, right? In this particular problem, you want to find the distance between 7, 7 and 4, 3. We want this blue line segment length. Okay, so let's figure out what these numbers are. Let's just think about x. Here's our x value of 4, and it goes all the way over to an x value of 7. That's 3 over. And now I'm at a y value of 3, and I go up to 7. That's 4. And again, you can think about the length here. You're 4 over 3 to get to 7. You're at a y value of 3, and you go up 4 to get to 7. So now I have a triangle. Now I can just bust that out. If I want to know that length c, I can say that 3 squared plus 4 squared equals c squared. 9 plus 16 equals c squared. 25 equals c squared. And then I take the square root of both sides. In this case, I'm only interested in the positive version, so you don't need a plus or minus because it's a length. And the square root of 25 is indeed 5. And I found that distance. Again, you're going to use the Pythagorean theorem for all of these situations when you want to find the distance between 2 points on a coordinate grid. This one happens to be a Pythagorean triple, which is kind of a cool one, right? It's a special one because it's got integers, 3, 4, 5. They're not always going to work out like that. They can end up being some irrational number, like the length could have been the square root of 11 or the square root of 17 or the square root of 15, right? You're not always going to get 5 or 7 or 6, right? You're not going to get an integer, but a Pythagorean triple will. I'll give you another triple. Okay, let's do another one. And we're going to do a bunch of these. You can get them all set. We'll use some negative ones here. Okay, how about that one? That looks like, I don't know, -7 and then -3, right? Left 7, down 3 maybe. And then how about, let's go over to 5 and up to 2. Okay, does that look like 5 comma 2 maybe? Something like that. Again, it's not perfectly to scale, and I want to know that distance. Okay, what you're going to do is you're going to draw this right triangle every time. Go over and go down, and then we'll figure out those numbers. Okay, so if you're at negative, again, I'm always going to do the x first. Doesn't really matter, right? You could have went up, and then you could have went over, right? This distance and this distance are the same, right? It doesn't matter. Over and up or up and over, it's kind of like slope. So if you're at -7 and you go all the way over to a +5, again, I'm thinking x value, that means you went over 12. So that's 12. And you started at -3y value and you went all the way up to a 2y value, well, that's 5. Okay, once you've established these numbers, then you can find the distance using Pythagorean theorem. Remember, leg squared, 5 squared, plus 12 squared equals c squared. 25, 144. 25 and 144 make 169. Square root of 169 is c. And then that does turn out to be another Pythagorean triple, 13. So a 5, 12, 13 actually also form a right triangle. And I just picked these two because they kind of made it easy. Okay? The distance between 2 points is this. Okay? Now, I don't even want to show it, but I'm going to. The distance formula. If you ever see this distance formula, it's just the Pythagorean theorem in disguise. I wouldn't even write this down if I were you. I never will probably write it on the board, other than maybe one time. There's the distance formula. And think about what the distance formula is. This purple silly formula is just an overly complicated version of the Pythagorean theorem. Okay, how do you find A? How do you find one of the legs? How do we find this 3? Well, didn't we just go to 4 and we counted over to 7? Isn't that the same thing as just 7 minus 4? Wouldn't that just tell us the 3? We could subtract the x values to find that distance. Sure we could, right? That's kind of what we did in our head. Okay, that's what this does. 7 minus 4 is 3. Okay, how do we find this 4? Well, we started at 3 and went up to 7. Or, the same thing, we could have took 7 and minus 3 and got 4. Whoa, doggies. Don't forget that square there. That would have been silly. So we get the 7 minus 4, 3 squared, and then over here 7 minus 3 to give us 4 squared. 3 squared plus 4 squared, square rooted, would have given us the 5. Right? What do we do? We square one, we square the other, we add them together, and then we take a square root. That's exactly what this purple is saying. Again, you can choose. The purple is the Pythagorean theorem in disguise. This would be referred to as the distance formula. It's kind of telling you what to do. But for me, I don't think you need told what to do. I don't think you need to be told how to find this length of 3 and this length of 4, nor to square it. And of course, then the last step is square rooting. But that's the distance formula that you're going to see. Okay, let's do 2 more, and then we'll wrap this up. This whole video is just about finding the distance between points. Okay, let's make this maybe a little harder. Let's get a, I don't know, how about we do a situation where I'm asking a question? Okay, how about this point right here? That looks like 6, -4. And how about this guy right here? Let's make it 9, comma, looks like 5. And then maybe this point way over here. I don't know. Let's make it -3 and 4. Okay, so the question I want to know is, Are those line segments congruent? Or is the blue bigger than the red or the red bigger than the blue? Remember, you can't go based on my picture. I said if you go on my picture, I'd maybe say that the red's a little bit bigger, but I don't know. The picture, I just drew it, right? So let's figure out exactly how big they all are. So let's use the Pythagorean theorem. Let's do the blue one first. Dot, 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 dot. Again, dot them, whatever color you want. Let's figure out these lengths. 6 to 9, that's 3 over. -4 to 5, that's 9 up. So the blue is 3 squared, 9 squared equals the blue c squared, meaning the length of the blue. So that's 981 c squared, that's 90. Ooh, this one's a good one too, because the square root of 90 we can work on simplifying. So you might want to watch another video on simplifying radicals. 90 can be written as 9 and 10. The square root of 9 is 3, and we get 3 square root of 10. That's in simplified radical form, and that's just the square root of 90, which will still be nice to know. Square root of 90, well, I don't know. It's not 10, it's not 9. It's probably something like 9.5. Okay, now let's do the red. Let's see if they're congruent, and if they're not congruent, then which one's bigger. So draw these guys. And it doesn't matter where you start. You can start here at 6 and go all the way to -3, which would be going 9 down, or you could have started at -3 and walked your way all the way up to 6. Either way, that's 9. And then -4 all the way up to 4. Oh my goodness, that's 8. I already know this one's way bigger, right? This is 3 and 9, and this is 9 and 8. This one's going to be way bigger, the red is. And so we were right in that case. It's way far left and up, where this one's just a little bit to the right and up. So over here, it's 8 squared plus 9 squared equals its own c squared. So that's 6481 equals c squared. Oh, and what is that? So that's a 5, and that's what, 145 equals c squared. And that's 5 and 29, so it turns out that that actually doesn't even get any better than that. But certainly the square root of 145 is bigger than the square root of 90, so the red is bigger than the blue. So we can solve more than just finding distance. We can ask, are things congruent? Which ones are longer? And then another cool one we can do, all right, I'm gonna use this same picture. Check this out. Well, I'm gonna try to draw that same picture again, and I'll talk you through it. So see this point right there? This point right here that we just found, and that point right there. Okay? So up here, this is A, B, C. Same points. Except now, let's say they form a triangle, which they do. Find me the perimeter. Oh, cool. Check that out. The perimeter, well, the perimeter is the distance around something. Well, I already know this guy. We already found this guy, right? That was this blue, right? Check this out. It's that same picture, right? That triangle. So this guy was the square root of 90. This guy was the square root of 145. All I'm left to do is to find this AC. And although it might not look like a triangle, it is. So look at this. I can do its own little triangle between A and C so I can find that distance. Now look at A. A goes from -3 all the way to 9. That's 12 over. And then it was 4 to 5. So it's a little 1. So it's a 1 squared plus a 12 squared equals its own c squared. 144. Check that out. 145. Even though it's totally different dimensions, it's still the square root of 145. So this red here is also the square root of 145, and then you would take this plus this plus this. You probably would turn them to decimals, and then you know the perimeter of a triangle. Again, we're not going to go into area of things, but you could also then find the area of rectangles or triangles or trapezoids in a coordinate plane, because once you can find the distance between points, you can answer all sorts of other questions, right? So, major cases. Easy ones, right? The distance on a number line. In 2D, the two examples on the front were Pythagorean triples where they worked out the 3, 4, 5. the 5, 12, 13. There's other ones, the 6, 8, 10, all different cousins of the 3, 4, 5. Right? We call those Pythagorean triples. They're just integer solutions, but they don't have to be. They can be in any quadrant. And really all you need to be able to do is to find this particular distance right there, is to find how much over and how much up, and then you can go to the Pythagorean theorem. And again, we can use the Pythagorean theorem because we always know we get that right angle because the x's and y's are always perpendicular. I think that's probably all we really need to do on this particular one. Again, there's some other things with area we can do later on in the world, but right now we can just use the Pythagorean theorem.